All right. So just to recap the notes from the last lesson, we talked about what acids are and what bases are. Acids are proton donors, so they're going to be donating a hydrogen ion into our solution. The pH of this is going to be a low number, so below 7. Other things to note about acids is that they are sour in taste. If you do taste any acids, and you guys have tasted acids, we were talking about what your favorite chip flavors were. And vinegar is an example of a weak acid that we can eat, and it has that sourness to it. So that's just some things to note about acids. You also come across acids when you're dealing with lemons, that sort of thing, so you have eaten them. Bases, on the other hand, are the proton acceptors. Another way to think about a base is that it releases the hydroxide ions, and hydroxide ions would be proton acceptors, because if they gain the hydrogen ion, they form water. So both of those are acceptable definitions. The thing to think about this case is that its pH number is going to be really high. So it's going to have a low concentration of hydrogen ions, high concentration of hydroxide ions. Do you want me to add that to the notes? Would that help? Yes? Okay. Let me grab my pens then. So I'll add a couple more things that you guys have asked. Acids would have a high concentration of the hydrogen ions, low concentration of the hydroxide ions, if we were wondering. And then with bases, it's going to be the opposite. High concentration of the hydroxide ions, low concentration of the hydrogen ions. Just as an extra added thing. With bases, they taste bitter. If you ever got your mouth washed out with soap because you swore, that's that taste. Soaps are an example of a base. Bases also feel slippery as well. If you have ever touched bleach, you would have noticed that's quite like a weird texture in comparison to other things. And that's because it's a base, so it's going to feel that slipperiness to it. We also talked about amphoric molecules, which have both acidic and basic properties. A good example of that is amino acids or water. They can be both proton acceptors and proton donors. So you do see that a couple of places. All right, keep moving it. I'll scan all these notes later, and you guys can steal this piece of paper if you want to have a look at it. The other thing that we started talking about was some of the other terminology. So that was acid base and conjugate acid and conjugate base. So when we're talking about acids and bases, we're talking about those reactants. Are they donating or accepting the proton? On the flip side of the products, then we have labeled things as conjugate acid and conjugate base, because we're mindful that now that we know that reactions are reversible, if that reaction is going in reverse, how would we label things as acid and base? So it's important to know that. So basically, conjugate, you just add to say this is the product, and it's acting as the acid in this case. So if I had this reaction with hydrochloric acid, in this case, the hydrochloric acid is the acid that's donating the hydrogen ions to the water. The water then becomes H3O+, and then there's the chloride ion. This H3O+ is what's going to be able to donate the hydrogen ion back to the hydrochloric acid and the conjugate, so making it the conjugate acid, and then the chloride is what's going to accept that hydrogen, making it the conjugate base. That terminology is going to be important when I talk about buffers tomorrow and what buffers are. So just kind of keep that in mind. And the last thing we talked about in the lesson was looking at pH and what that relationship is. So pH is just a measurement of the hydrogen concentration. I've given you the two equations that come up for that and how to convert from one to another. Again, if you're coming across this information when you're looking at it, when you're reading. The main thing to kind of keep in mind is talk about that industrial revolution and how the pH of the ocean has changed. So the industrial revolution, we're talking about maybe about 100, 150 years now. And in that time frame, our ocean pH has gone from 8.2 to 8.1. It's a 0.1 difference, which most people will go, that's 0.1, that's not very big of a difference, but you have to remember this is the pH scale, and it's logarithmic, so 0.1 is actually a much larger number when you factor in logarithmic scale. It's roughly an estimate of 30% drop in the pH of the oceans. We suspect that if we continue with this, over the next century, so another 100 years from now, if we don't make some changes, that pH can drop to 7.8 or 7.7 is what we're estimating it to be based on our current projections. Really scary and dangerous because that's actually the lowest it has been in over, 20 million years. So that is concerning, and we're going to see in tomorrow's lesson how does that impact the sea creatures and things like that. How does it impact economies, et cetera, et cetera. So, like I said, I think when we introduce this topic, we talk a lot about climate change and what's happening at the surface level, but we also need to think about what's happening at the ocean level as well. All right, so that's that. Let's now talk about I'll put this on my desk if anyone wants to steal it for now. Let's talk about what we saw yesterday. So, when we are thinking about acids and bases, we are thinking about their dissociation. So how are they breaking apart in water? So if I have hydrochloric acid, which is our strong acid, and we've already seen this, if I add it to water, it's going to dissociate and release the hydrogen ions and a chloride ion. Are you okay with that so far? The other acid that we did was ethanoic acid, which is CH3COOH. You guys would have seen this from organic chemistry. And it dissociates, it loses that hydrogen ion and becomes CH3COO minus. And you guys would have seen this when we were doing our organic chemistry topic. Are we good with that so far? Now, dissociation is how well does that break apart and release those hydrogen ions? Because it's not an acid until that hydrogen ion's free. So this here with the hydrochloric acid is a strong acid, and that's because there's full dissociation. So it fully goes in the forward direction, releases all its ions. For the ethanoic acid, it is a reversible reaction. So when it hits equilibrium, the forward and the reverse reaction are possible. But the thing to remember about this one is that this does not fully dissociate. So that doesn't fully dissociate. And that's really important when we're thinking about acid strength and reaction, because if it doesn't dissociate, I don't have those hydrogen ions. And those hydrogen ions are what specifically is making something an acid. Are you okay with that so far? So in Monday's experiment, both of these were at the same concentration. So they both have the same amount of this available. But they had different strengths and reactions because of the dissociation. So hydrochloric acid was fully dissociating, the ethanoic acid wasn't. And so since it wasn't, we didn't have as many hydrogen ions there to make the pH indicator go full red, and it wasn't available to then react with the magnesium metal. Does that make sense? And so even when we had hydrochloric acid at half the concentration of the ethanoic acid, even though it had half the amount of HCl, since it was fully dissociating, it had more hydrogen ions available to it than the ethanoic acid did at 1 molar, twice the concentration. Are you okay with that so far? We good? All right. So I want to show you guys an equation then, so that way you are aware of how do we then calculate the pH for a weak acid. So these calculations that I have here are assuming full dissociation. So this is for full dissociation. So strong acids, strong bases, those would all work. When I have a weak acid and I want to figure out pH, if I want to figure out the pH to a weak acid, the equation changes to being a half of the pKa value minus the log of the concentration of the hydrogen ion. Actually, I should say log of the acid concentration. So that's the weak acid concentration. Now, some of you guys might be wondering, what does that pKa mean? So pKa is referring to the equilibrium constant for the acid, so the dissociation of it. So I can find the pKa by doing the log of the Ka. Ka is referring to the dissociation constant. Now remember, you don't need to do any of the calculations for this assessment. I'm just pointing them out in case you come across them when you're reading, or if you want to use it in your essay to show your chemistry understanding. So for each acid, I would have a dissociation constant, and I would take that number and do the negative log to get the pKa, and then I could plug that into the equation. And if I know the concentration of that acid, say it's 1 mole per liter, then I could do the calculation for what the pH would be. Are we okay with that so far? You don't have to worry about doing any calculations for this assessment. I'm just pointing it out in case you come across it, or if you do want to use it in your essays. So if you're reading about carbonic acid, you can look up the Ka of it, and you can do the math behind it. Or if you've been given the pH of the ocean, you can work forward and talk about what this value is. Are you right so far? All right, what questions do you have? Do you guys want me to show you the equation for the ocean acidification now, or should I hold off till the next lesson? You want to do it now? Okay. I'm going to get a bigger piece of paper, and I'm going to turn it sideways so that way you can see it, because it's a big, long equation. So we have to remember there's lots of sequences in the ocean acidification equation. So the first thing we got to think about is that we have carbon dioxide as a gas, right? Move that over. So we have carbon dioxide as a gas in our atmosphere. Now it will mix with water from our oceans, which is a liquid. Are we okay with that so far? Now, you do this all the time when you're carbonating water. You're forcing carbonation into sodas and things like that. It's the same thing that we're thinking about with the ocean acidification. The carbon dioxide gas is getting mixed into the water. This is a reversible reaction. When it does that reaction, we form carbonic acid. So C2CO3, and that's aqueous. So that's your carbonic acid. Are we okay so far? All right, next step then. So now I have my acid molecules in the water, and we know that acids dissociate. This one is a weak acid, so it will dissociate and reform. When it dissociates, it releases the 1 hydrogen ion, and then you form bicarbonate. Both of these are aqueous. Or hydrogen carbonate's the other word that you would have seen. Have you guys heard of bicarbonate somewhere? Where have you heard about it? Baking soda, yeah. Yeah, and you would have heard of calcium carbonate as well. All right, and then this also will further dissociate as a second step, and we can release an additional hydrogen ion, and you get the carbonate. So that's everything that's happening with that reaction. why is that carbonate special and important in our oceans? Does anyone know? Blake, you might have an idea.
I kind of know, but I don't know it.
You said calcium, right?
I said calcium. I said something rather than calcium that makes the ocean more basic.
Yeah. So this here is important for sea shells.
Oh, yeah, that's right.
Yep. So we need carbonate for calcium carbonate to make shells. Shells, coral, the whole shebang. Yeah? All right, so this is a wee bit of a problem when it comes to climate change. So when we're thinking about this whole equation here, and we're thinking about disrupting the equilibrium, when we have lots of carbon dioxide in the atmosphere, what direction is it going to force the reaction to go to restore equilibrium? Forward, and it's going to make carbonic acid. And then that carbonic acid is releasing these hydrogen ions. So what's going to happen is it's going to basically force it to go somewhere in the middle of this equation, so that way it uses up the hydrogen ions. And then we're going to lose those carbonate ions, which is really, really bad because we need that for the shellfish. Does that make sense? So we're looking at this equation and we're thinking about how is the different things changing, affecting the direction, and then thus the ocean acidification. There's a simplified way to think about that equation if you want to use, and that is CO2, which is your gas, plus H2O, which is your liquid, plus calcium carbonate, which is a solid. What's going to happen is we form calcium ions and bicarbonate. So if we increase that carbon dioxide, it's going to force this reaction to go forward, using up that carbonate, which we desperately need in order to make shells. So now you can start seeing how this fits into what we've been talking about with equilibrium and with weak acids and bases. So this carbonic acid is a weak acid. And the reason why I know it's a weak acid is because it's doing all of this reversible reaction. So that's good news for us because we can manipulate equations if they're reversible. But the problem is right now we're not doing a very good job because we keep increasing the sky here. All right, what questions do you have? Why do we need shells? Well, you're going to research that and find out why. Yeah. You need them for sea creatures, such as mussels and oysters, coral as well. Yeah, shells were once housing sea creatures. Yeah? And the other thing you're going to be thinking about is the food chain. And where does this stuff fit on the food chain? So you guys are going to research that. That's your essay. But don't go too far down the biology route with the essay, because it is still a chemistry essay at the end of the day. I was like, oh, yay, biology!
What is the,
Yeah.
the state of the calcium carbonate?
This one? Yeah, so they should be aqueous.
No, in the simplified one. What is that?
Oh, that's solid.
Oh,
Technically it's solid.
okay.
Yeah. These are all aqueous. Yeah. So we're talking about solid shells that start getting dissolved. Yeah. And so tomorrow's lesson I'll talk about buffers and what buffers are and how we're running out of buffer and then why the shells are getting dissolved. It is not good. All right. Cool. Can I move it? Yes. Yeah, I'm going to scan all of it later. Do you want a photograph of the stuff? All right. Can I move this?
Yeah.
All right. Oh, wait, you can take this one too.
Yeah.
Just give it back. All right. It's going to pop.